All right, we've started recording. Okay, yes, set. All right. So in the previous class, I had started discussions on these examples, very straightforward examples. First, starting with this cantilever beam under a tip loading, and then I had moved on to this simply supported beam, which is under uniformly distributed load. And I had mentioned that these kinds of problems we can solve by different approaches. And this particular problem I had solved using this fourth order differential equation, while the previous problem I had solved using this equation. Please note that these are like different versions of the same story. Okay, it's not that they are different equations. I mean, of course, they are different equations, but it's not that they convey completely different information. It's not like that. Now, depending on the nature of the problem, we'll have to select which is the best approach. Okay. As you can see, there is another version of this equation which involves this shear force, EI d cube y dx cube. But in practice, I have never personally seen this equation being used ever. Okay, either this first version is used involving the m, that is the second order differential equation, or this fourth order differential equation. In fact, as you move on to higher classes, you will see that when people refer to the equation for a beam to find out the deflection of a beam, they usually refer to this fourth order differential equation. In fact, when we move on to the next chapter, which is buckling, and you go on to more advanced theories involving buckling, you will see that the equation which, or the theories which involve the buckling, they involve this kind of a fourth order differential equation, of course, with another term. Okay, so I think it is a good practice to keep in mind and to try to solve this fourth order differential equation and to regard this as the more general form. Now we will consider another problem. We'll consider a number of problems, but just to illustrate a couple of new things, let me just take this problem. Another simply supported beam, but okay, by means of providing these rollers, I am ensuring that this is a statically determinate case. I will be taking up statically indeterminate cases a little bit later. So the loading will be like this, P, and this distance, the entire length of this beam is L, and this distance is L by 4. And we are supposed to determine the equation of the elastic curve. The equation of the elastic curve basically means that you are supposed to find out the values of the deflection of this beam under the influence of this loading and these supports as you move along the length of the beam. That is what is meant by that. Okay, equation of the elastic curve. So tell me what I can do here. Tell me what is the first step I need to do here. This is the reason I'm asking you this.
Find the reaction.
Find the reaction forces. Okay, so tell me quickly what are the reaction forces at the left end and the right end. So if I draw the free body diagram of this beam, removing the supports, it's going to look like this. there's going to be R1 here, and there's going to be R2 here. There's also going to be a R horizontal force here, a horizontal reaction force here, but you know, through the simple application of the sigma Fx equal to 0, that horizontal force is going to come out to be equal to 0. So tell me, what are the values of R1 and R2?
R1 is 3p by 4 and R2 is p by 4.
All right.
Yes.
So R1 is equal to 3p by 4 and R2 is equal to p by 4. So these factors that you see, they are coming out inversely as their corresponding lengths. So okay, so this 3 by 4 thing is coming out as this 3 by 4, and this 1 by 4 is coming out as the other one. Okay. And you can of course find out by taking these the moments about this one and the moment about this one. All right. Now what do I do? So please take a look at the previous pages, maybe this one. So what we did here, we took a cut section at some generic distance x from one of the ends, and we considered the expression of the bending moment that is present over that cut section, and we expressed the equation, this version of this equation, ei d square y dx square is equal to m. That m we expressed in terms of that internal moment. So can we perhaps do something similar in this current example? Please tell me. Where should I take the cut? If I want to find out the internal bending moment, where should I take the cut? Any suggestions?
So we need to take two cuts in that case, one between 0 to L by 4 and one between L by 4 to L.
Yes, very good. So you see, the situation is a little bit different here. In the same way that you encountered the difficulties associated with finding out the bending moments and the shear force diagrams, it is the same kind of situation here. Because the way that the bending moment needs to be calculated in different portions of this beam is going to be different depending on where you take the cut. So for instance, I have two cases here. One is between x equal to 0 and x equal to L by 4. So if I take a cut at some generic distance like this, the part of the beam that is going to be exposed, so for 0 less than x less than L by 4, the free body diagram of this portion of the beam on the left of this cut, it is this. I have my R1 present over here. I do not have the influence of the P on this portion of the beam. Rather, what I only have is this internal shear force V and this bending moment M. And if I take the moment balance about an axis which is passing through the right end of this cut portion, then what am I going to get? This is M minus R1x is equal to 0. Please note that this portion now is my x. So from here, I obtain M is equal to 3p by 4x, which means that with regards to my equation, the concerned expression on the right hand side is going to be so I have ei d square y dx square is equal to m. The m expression is this, so I just substitute it here and I can go on to solve this equation. You can all do this. Of course, there is there's the question of what boundary conditions And we are going to come to that discussion properly a little bit later. Next, what I'm going to do is consider the x between L by 4 and L, which means that this time I'm taking the cut here. So my free body diagram of the left portion of the beam, or the portion of the beam towards the left of this cut, is going to look like this. I have my P over here, and just like before, I'm going to consider the internal shear force and the internal bending moment like this. Please note that now my x is this entire x, and this portion remains L by 4. Now again, I want to find out the expression of the m here. So again, I considered the moment balance about an axis which is passing through the right end of this cut portion of the beam. And then I'll have m minus r1x. And the contribution from this P will be what? Tell me. In this equation,
x minus L by 4.
X minus L by 4
is going to be plus P into x minus L by 4. And this is going to be equal to 0. So I will get a certain expression for my m. What is it? Tell me. If I substitute the expression for R1, ultimately, what will I get for m? Tell me.
PL by 4 minus PX by 4.
PL by 4 minus PX by 4. Yes. So that can be written as minus P by 4 x minus L. All right. Which means that earlier my concerned equation was this. Now my concerned equation is this. Okay, so this is the form of the equation between 0 and L by 4, and this is the form of the equation between L by 4 and L. We can solve this equation, find out the expression for y, which is valid between for x between 0 and L by 4. We can also solve this equation and find out the expression for y, which is valid for x between L by 4 and L. Now, this itself is a second order linear differential equation. When you integrate it twice to find out the expression of y, you are going to end up with how many constants of integration? Unknown constants of integration? 2. So from here, you are going to end up with something like C1 and C2. And here also you have again a second order linear differential equation. Okay, so when you correspondingly integrate it twice to obtain the expression for y, you are going to end up again with two unknown constants of integration, C3 and C4. Question now boils down to how do you go about finding C1, C2, C3 and C4? The point that I want to highlight here is that you please make a comparison with our earlier problem. This example number 1. Here we had one form of this governing differential equation, this equation, and after finding this out, we ended up with these two constants of integration, and we were able to use these two boundary conditions to obtain the values of C1 and C2. Okay, now we are again ending up with second order differential equations, but because we have two forms of the equation, mind you that we are still talking about the same beam. Okay, same beam, but two forms of the equation in two different regions. Correspondingly, we are ending up with four different constants of integration. Okay, so it would seem that we need four boundary conditions. Okay, because we have four unknown constants, so definitely we need four conditions. What are those four conditions? That is my question to you. Try to think. Yes? Someone said something. What are the four conditions that I need to use to obtain the values of this unknown constants C1, C2, C3, and C4?
Y equal to 0 at x equal to 0 and x equal to L.
Very good. So definitely we can use that. Let's go to the next page.
Answer dy by dx 0 at the point P. Like,
wait a second. So to find C1, C2, C3, C4, we need four conditions. All right. So first of all, you are saying that at x equal to 0, y equal to 0, at x equal to L, y equal to 0. So there can be absolutely no confusion about these two conditions because it is guaranteed that these two are pinned ends. There is no way that there is going to be any deflection of the beam at this end or at this end, which basically translates to the fact that y is equal to 0 at both x equal to 0 and x equal to L. What was the other condition someone mentioned? Tell me.
so dy by dx 0 at the point where P is applied.
How do you know that?
So y equal to L by x equal to L by 4, the both equation will be the same, and dy by dx will also same, means continuity and differential both same.
Or m equal to 0 at x equal to 0 and x equal to L by 4.
Okay, so we have a difference of opinion here. So someone is saying here that at this point, x equal to L by 4, we need to ensure that y is continuous, and I think he mentioned differentiable, but I think what he actually meant was that the deflection should be continuous and the slope should be continuous because dy dx should be continuous. That is one version of the opinion. The other version, I believe, what I heard correctly, is that at this end, I think the other guy mentioned that the m should be equal to 0, and at this end, the m should be equal to 0. Did I hear correctly? The second guy?
Yes, sir. Yes.
Okay. Okay. Now, there is absolutely nothing wrong with the fact that m is equal to 0 here and m is equal to 0. Okay. By itself, there is absolutely nothing wrong with this condition. It must be true that this is a pinned end. There is no resistance to the rotation of the beam at this end. Therefore, the bending moment here must be equal to 0. Similarly, this is a pinned end. Even if this roller at the bottom doesn't matter, because this is a pinned end, there is not going to be any resistance against rotation. So the slope, so the bending moment here is also going to be equal to 0. But question is that despite the fact being true, despite the statements being true that m is equal to 0, does it really help us to solve our equations? You see something. If you suppose think, and please note that when this other guy was saying that m is equal to 0, he actually had a point, because earlier when we were doing this example 2, okay, when we were doing this example 2, we actually used something like this. Okay, because you see here at x, this was also a simply supported beam. Here we used x equal to 0, y equal to 0, x equal to L, y equal to 0. This same thing we are using now. And then for these two ends, we went on to use this m equal to 0 conditions. So if we can use these conditions here, surely we can use these conditions in the example 3 also, which we are currently doing. But there is a problem. Okay, there's a very subtle problem. Problem is like this. You see, what is the nature of the governing equation that we are solving now? Nature of this governing equation is a second order linear differential equation. Second order means this order of this derivative is 2. This order of the derivative is 2. Okay, in fact, these things are the bending moment expressions. EI d square y dx square, that is m. This is m. Now you see that suppose you have a differential equation like this. Okay, a general differential equation d square f dx square is equal to some g of x. Okay, this is a differential equation. If you integrate it twice, you are going to end up with again two constants of integration. Now the boundary conditions to this should be expressed how?
So in the form of g of x or integration of g of x like that.
No, I'm talking about the boundary conditions. What I mean to say here is that the boundary conditions should be expressed in such a fashion that those boundary conditions involve derivatives. If at all they involve derivatives with respect to of f with respect to x, they should be at most of the order of 1. I repeat, if you have to express your boundary conditions for a second order differential equation, then none of the boundary conditions should have an order greater than 1. Similarly, if you're solving a third order equation, then none of the boundary conditions should involve an order greater than n minus 1. Or if it is an order n equation, okay, so if it is something like this, where n is an integer, okay, so the boundary conditions should not be, okay, so their order of the boundary conditions should be less than equal to n minus 1. Why is it so? It is so because let's take a very simple case, okay, d square f dx square, this is equal to, let's say, 0. Simplest of boundary conditions. What is the solution to this? Tell me. This is c1 plus c2x. Fine. This is correct. F is equal to c1 plus c2x. If you integrate it once,
Yes.
you will get constant. This is okay. This is correct. Now you can definitely write down the boundary conditions directly, like at x equal to 0, f is something, and at x equal to L, f is something. Okay, and you will be able to solve it. But suppose you want to express the boundary conditions in terms of derivatives. So another option is that you can write it something like this, that df dx at x equal to L is equal to something. That is another boundary condition. So if you utilize these two conditions, you will again be able to solve for C1 and C2. That can be done. But suppose you say that no, my boundary condition will be like this, that d square f dx square at x equal to L will be something. There is nothing wrong with saying this, but does it really help you to solve this equation? It doesn't. Why not? Because you see, this f is of, you're obtaining this f from solving this equation d square f dx square is equal to 0. This has already a certain value. Again, if you do this d square f dx square, you're going to obtain this 0 only. Okay, basically what is going to happen is that if from an nth order differential equation you find out the expression of the f or the dependent variable, and then you go on to express the boundary conditions again of that same order, you are going to lose all the constants of integration. But your job or your intention of using the boundary conditions is to find out the values of those unknown constants. Okay, so if you go back to this thing, and from the expressions that you obtain for y and y here, you apply something like this, that at x equal to 0, m equal to 0, at x equal to L, m equal to 0, that is fine. Okay, that is fine. But it is not going to help you to solve for C1, C2, C3 and C4. Okay, and you can quickly check that these two conditions are actually identically satisfied by these governing equations themselves. You just substitute x equal to 0 here because this is valid between 0 and L by 4. You substitute x equal to 0 here. This is x equal to 0, so this expression is equal to 0. And this is actually the expression for the bending moment, so m is equal to 0 at x equal to 0. Similarly, for the region between L by 4 and L, this is the governing differential equation. So you substitute x equal to L here. This is equal to 0 on the right hand side. On the left hand side, you have the expression for the bending moment. So this expression is identically valid. Okay, this m equal to 0, these two conditions are identically satisfied by whatever you have. So you're not getting anything regarding the values of C1, C2, C3 and C4. Okay, so they do not help us in solving for C1, C2, C3 and C4. So there was another opinion here that we should use the continuity conditions, and that is the correct thing that we are going to use. So what we are going to say is that at x equal to, let me write it in a different fashion. So continuity of deflection and continuity of slope must be maintained. Between the two regions. Between the two regions means we have two regions here from 0 to L by 4 and from L by 4 to L. So between these two regions, the common interface is at x equal to L by 4. So at x equal to L by 4, that common interface, we must have that y coming to L by 4 from the minus side is equal to y at x equal to L by 4 coming from the plus side, and dy dx. So dy dx, you please understand that this is the slope. This at x equal to L by 4 coming from one side is going to be equal to dy dx at x equal to L by 4 coming from the other side. Okay, so these two conditions must be satisfied. This is a very, very important fundamental concept. In many problems, you will see that in addition to the conditions which are present due to the reaction supports, in addition to that, you will have to ensure that this continuity of deflection and the continuity of slope are maintained. Okay, this is extremely important. Okay, in many different problems, you will have to use this. Yes.
So like, why can't we have sharp bending? Sir?
Why can't we have
sharp bending? Like there will be something like a corner, and then that the continuity of slope won't be there.
So right. So you are saying that why can't it have something like this kind of a way? Yes, this kind of a deflection.
Yes, sir.
Okay. So for in order to understand these things, like very formally mathematically, I'll have to appeal to elasticity theory, okay, which you have not done. But the way that this is usually explained at the undergraduate, at the second year level, is that this kind of a deflection is completely unphysical. Okay, meaning that you are never ever going to observe these kinds of things in practice. Okay, so this is This is presented to the students, and I am presenting to you right now as an empirical fact that this is never observed in practice. Okay, but we can go about trying to do these things in a very formal mathematical fashion also. Right now, this is not the time and place. Okay, so please understand at this moment, accept this thing as an empirical fact. Okay, that in a real beam, you will never see the deflection changing abruptly like this at a certain point. All right.
Excuse me, sir.
Yes.
So at x equal to 0 and x equal to L, m is equal to 0. So in previous problem, in second problem. So why is it working?
Second problem. This one.
Yes, sir.
Yes.
Why is it working here?
Why is it?
Means
Yeah, because
we are using
the governing differential equation was this. It was a fourth order differential equation. Okay, so n was equal to 4. And in none of the boundary conditions, we are using the order of the equation as n equal to 4. The highest order is 2 here. Okay, the order of the differential equation is 4. The highest order in any of the boundary conditions. So here it is 0. Okay, there is no derivative. It is directly in terms of the dependent variable y. Here the highest derivative is 2, which is less than 4, so no problem.
So,
Yes.
so suppose in example 3, we differentiated.
Yes. Yes.
We differentiated 3 up to 4 derivative.
All right.
Then we can use that m equal to 0 at x equal to 0 and L. And
Yes.
in addition to it, we have to also use continuous and derivative.
No. Listen. So suppose you decide at the very outset that you are not going to use this version of the equation. Okay, this is in terms of the m. You decide at the very beginning that I'm not going to do this problem like this. Rather, I will try to do this problem using that EI d4y dx4. What was on the right hand side? Do you remember? You can just check. This was w minus w. Right? Minus w. Okay, so even before starting about starting to think about the boundary conditions, you should be a little bit concerned about how do you express this w, because you see for this problem there is no distributed load. Okay, there is no distributed load.
Yes, sir.
So does it mean that we set w equal to 0? What do we do? Tell me. So this is like a general knowledge question, which has some relation. Okay, think about it for 15 seconds. I'll give you a hint. All of you, please think about it. That suppose some student decides that no, sir has at the beginning of the class, sir has said that the fourth order differential equation is the more general version of the beam deflection equations. So from now on, I am not going to touch the second order differential equation. I am only going to use the fourth order differential equation. But the very moment he starts to do this, he is encountering this difficulty that there is a minus w on the right hand end. But there is no distributed load here. So, I mean, it's like a dilemma now. What to do? You think what to do? Think for a few seconds, I'll give you a hint.
So why can't we take it as 0 and then integrate?
You want to take it as 0. W is equal to 0.
Yes, sir.
All right, and then what? See, suppose, okay, you reason like this. Okay, you are solving one problem. Okay, you want to do some maths, you want to do some differentiation, integration. Okay, IITians are always fond of doing these things. Okay, जहाँ भी देखो equation मिल गया, start doing differentiation, integration, putting boundary conditions. By the time you reach your fourth year, you will be absolutely experts in doing this. Whether it is in fluid mechanics or in mechanics of solids or heat transfer, you will be encountering number of differential equations. So the moment you see a differential equation, you feel you are the king of the world. Okay, but it is always a good idea to think a little bit physically also what you are trying to solve. Okay, doing maths is fine. I also like doing it. But what you are trying to solve? You are trying to solve a beam problem where the loading is given by the P. Suppose you put this thing as 0. Are you not losing completely the information about the loading which is bringing about the deflection?
Sir?
Yes.
So can I transform this concentrated load into a distributed load?
How? Your thinking is in the right direction actually. Okay, your thinking is absolutely in the right direction. But tell me how.
So like in a distributed load when it's given, so in the problem first we change into concentrated load that by them multiplying with the length and also finding the point where it is acting. So if we do it in the reverse way.
How? Tell me how. The reverse way is actually not that straightforward. Okay, because you have infinite number of ways of doing that. If you have a distributed load, you have a unique way of replacing it by a concentrated load, is it not? But doing it the other way around, you have infinite number of options. Which one will you take?
Sir, is
So
it
we will consider the W in the region L by 4, 0 to L by 2. And W is equal to P upon L by 2.
Say that again, I could not hear.
So we will consider the distributed loading in between 0 to L by 2. And W will be P upon L by 2.
So you guys are thinking about distributed loading, literally like distributed loading, like you want to take this big arrow and you want to literally distribute it over, sprinkle it over this thing. That's what you are thinking. Okay, I'll give you a hint.
So Dirac delta function is it?
That is the hint I wanted to tell you. Who said this thing?
So Niranjan.
Good, very, very good. That is the correct answer actually. So the mechanical students and the manufacturing students, I believe, are both doing transform calculus in this semester. Yes?
No, sir.
No, sir.
Yes, sir. No, sir. I'm only talking about the 20 ME and the 20 MF.
So we have it.
Manufacturing students don't have calculus.
Which students?
Manufacturing students. Probability and statistics.
Really?
Yes, sir.
So in mechanical, we have partial differential equations. We don't have transform calculus this time.
So your syllabus is not actually properly written in the website, right? The 20 ME students, you are not doing transform calculus.
Sir, I think we have it next semester.
Please, only one of you say, okay, there's a big confusion. Let me be clear about this. The 20 ME students, okay, MF students, you don't reply. The 20 ME students, are you doing transform calculus this semester? Yes or no?
No, sir.
Okay. 20 MF students, are you doing transform calculus this semester?
No, sir.
Okay.
No, sir.
What about, who said yes? Answer is no. Okay, all right. So 20, the QM students, the QDM students, are you doing transform calculus?
No, sir.
Okay, thank you. Anyone else, any other group is left in this class? Okay, so officially the transform calculus thing you have not done. You have not, I mean, well, maybe a little bit of these things you have encountered as part of your physics classes, the Dirac delta and the heavy side, but properly you have not done. Okay, so it's good. Okay, so there is a topic within the deflection of beams chapter. You may have already seen it in your textbook. it is referred to as beam deflections using singularity functions. So singularity functions basically uses the Heaviside step function and the Dirac delta function. Okay, they call it singularity functions, but it's basically that. Okay, so I am officially leaving that out of the syllabus. Okay, I was under the impression that ME and the MF students are doing transform calculus, but the QDM students are not doing transform calculus, but it seems that I was completely wrong. None of you are doing transform calculus. So it's good that I am leaving that out anyway. But do remember that using singularity functions, it's actually very, solution of many of these beam deflection problems, it becomes very easy, especially if you want to code it up in symbolic mathematics, either in MATLAB or Python. And both MATLAB and Python, they have inbuilt inbuilt functions which can represent these singularity functions. Okay, both the Heaviside and the Dirac delta. So life becomes very easy then. Anyway, I'm leaving that out, but I'm just saying to you for general knowledge purpose that this P, just like Niranjan had just said, it can be written as a distributed function using the Dirac delta. Okay, so this W, you do not have to literally think of it like a distributed load with a bunch of arrows sprinkled over here. Rather, you can think of this W as P times the Dirac delta. Okay, so if you have some idea about the Dirac delta, you will understand what I'm trying to say here. But let's not go into that into more detail. You just understand it like some kind of general knowledge. Let me remove this thing. So to go back to the original question which was asked, we can solve this equation or any other equation using the fourth order equation, definitely, but we have to be a little bit careful on what or how we represent the loading on the right hand side. Okay, so does that answer the question which was initially asked?
Yes, sir.
Okay, let us move on. So I have prepared a few problems for the tutorial sheet, but I will come to that a little bit later. First, I want to discuss a few other things. Well, you see, we have been talking about different kinds of supports. Okay, first of all, we considered this exercise 1, where you understood that this was a fixed end, and I told you that at the fixed end we have this y equal to 0 and the slope equal to 0. We moved on to these simply supported beams, where we had to contend with this pinned supports, and conditions which are present there at the pinned supports are that the deflection is 0 and the bending moment is 0. Although depending on which form of the governing differential equation you are using, you may or may not get to use the m equal to 0 condition, as was illustrated in this example number 3. Now, beyond these, there can be some other kinds of beam ends. What I mean to say is that let us tabulate the very commonly encountered end conditions, because it will help you to solve different kinds of problems. Okay, so it's like this, that we have already encountered the various kinds of boundary conditions. So we have already seen the pinned end. Let me write the clamped or the fixed end. So it's like this. This is the end of the beam. And for here, I have y equal to 0 and dy dx equal to 0. This we have already seen. Next, pinned or hinged end. So it's like that. And for this, I have y equal to 0 and m equal to 0. And this m equal to 0 translates to ei d square y dx square is equal to 0. Next, I have something called the free end. Free end is like this. Okay, there is no attachment anywhere here. Okay, it is just like floating in the air. Of course, the other end has to be attached to something. It has to be fixed to something. Okay, so this end is free. So can you tell me what will be the corresponding boundary conditions for this free end? What are the things that should be 0 here? Definitely you can try to understand physically that if this end is free, then there is no constraint on the deflection. Deflection can be anything. Okay, in general it is not going to be equal to 0. So we cannot say anything definitely about the deflection. Similarly, we cannot say anything about the slope also. Okay, depending on the kind of loading that this beam will be subjected to, and depending on the condition which will be present on the other end or along the length of the beam, the deflection and the slope may be whatever the situation demands it to be. So we can never say for sure what is the deflection at this end or the slope at this end. So what can we say? Can we say about anything about the bending moment? So m is going to be equal to 0 here. Okay, m is equal to 0 here because there is no resistance to the rotation here, which means that again I have ei d square y dx square is equal to 0. The other condition is that the shear force must be equal to 0, and which translates into ei d cube y dx cube is equal to 0. And you have already encountered this earlier when we did this. You see, from here, if we differentiated once, we obtained this dm dx, and this dm dx was nothing but v. So ei d cube y dx cube is equal to v. Okay, this is what I'm using here. So from the physics of the problem, I am saying that the shear force is going to be equal to 0 here, and from that I'm going to state that ei d cube y dx cube is equal to 0. Now, just like earlier we had seen that if we are using the form of the governing differential equation which starts with ei d square y dx square, then we cannot use either this one or this one, okay, as our boundary conditions, because the order of the equation is 2, this itself is 2, and this is even higher order. So these two conditions can be used only when we are using the 4th order differential equation version of the governing differential equation. Please remember that. Next, we have another kind of boundary condition, which is referred to as the guided support. Even you can have slightly different names for these. So it's like this. So this part is the beam, and to the end of the beam, some rollers are attached, and these rollers, they move over this kind of a wall. So tell me from the physical considerations, what should be the conditions at this end? You have actually encountered this situation back in the chapter on in one of the problem sheets earlier, the tutorial sheets earlier. I think it was the one on shear force and bending moment diagram.
Sir, moment equals to 0.
No, not moment. So actually it is shear force equal to 0. Okay, because of this rollers, there is no resistance against this vertical movement. There is no resistance against this vertical movement. So that the force along that vertical direction, that is equal to 0. So V is equal to 0, which translates into EI d cube y dx cube is equal to 0. What other thing? Is the deflection 0? Can we say that the y is equal to 0? Yes, no?
Sir, it's almost like a fixed end with respect to that rollers.
But this roller, it allows for the free movement of this end of the beam either in the positive y direction or in the negative y direction. Complete free movement in this vertical direction.
So we can say dy by dx is 0.
Yes. Okay, it is not the deflection which is 0. In fact, it is anything but 0 at this end. Okay, it is not at all 0, the deflection, but the slope is 0. Slope is 0 means that, you see, just like we have the fixed end where this, I mean, if you think of this beam end like this remains vertical and this part remains rectangular like this. Okay, this part remains like this in the fixed end. So also here, this part remains like this. Okay, so even though this may translate up and down, but very near to this end, this always remains rectangular like this. So this dy dx at this left end, that remains as 0. So these are the some commonly encountered boundary conditions. Okay. Now, I just want to highlight something, that this free end, it can cause a little bit of a confusion sometimes. For instance, if you have a cantilever beam like this and you have a tip loading. Now it may seem that since there is nothing attached to this right end, some of you may erroneously think that this is a free end. Okay, but please note that this is not free end. It is not a free end because if after doing the calculations you try to determine the shear force very close to this end, you will find that that is not equal to 0. But one of the conditions which is associated with this free end is that the shear force must be equal to 0. Okay. In fact, you will find out that the shear force is equal to the applied load at this end. So this is not a free end. Similarly, you can have another situation where you have another cantilever beam, but instead of a tip load like this, a point load like this, you have a bending moment, an external bending moment being applied like this. So this is some P and this is some M node. This also is not a free end. It is not a free end because you see the other condition which is associated with free end, that the M should be equal to 0, that is not true here. The bending moment at this end is constrained, or it is given to be equal to M naught. Okay, so this M naught is certainly not 0. So this is not a free end. Okay. All right. So moving on. Next, what we are going to discuss is something very, very interesting and something where the considerations of these deflections that we have been studying are of paramount importance in order to entirely solve the problem. So I'm referring to statically indeterminate beams. statically indeterminate cases. So I'll take a few minutes break here, okay? Because I'm not particularly well. My throat is also paining. So let's take maybe 2-3 minutes break. I'll come back after that. All right, let us start again. So we are going to start discussing the statically indeterminate cases. Now, as with the previous statically determinate cases, it will be best to explain these things by considering specific examples. So let us consider such an example. We consider a statically indeterminate beam, and I'll draw this thing and you tell me why it is statically indeterminate. Okay, so we have this beam here, which is fixed to this wall on the right end, and on the left end, it is pinned to this support. And I'm stating that this is a statically indeterminate beam. You tell me why.
Four unknowns and three equations.
Because what?
Like we have four unknowns and three equations.
What are the four unknowns here?
Mx, My, and the dx, like Mz, then Fy, Fx, and the reaction at the pin. Not the pin, the roller joint.
So at the pin, how many forces are there? Only one.
One force.
Yeah. At this end, what are the things present?
Two forces and one moment.
Two forces and one moment. So one force along the vertical direction and one force along the horizontal direction and one bending moment. So you have three unknowns present at this end and one unknown present at this end. So overall, if you consider the static equations of equilibrium, you will have only three equations from those, but you will have four unknowns to solve for. So if we compare this with our previous problems, there is immediately one big difference at the very outset, which is that consider this problem. The first step in solving this problem was to determine the unknown reaction forces which are present at the two ends, which we found out as R1 equal to 3p by 4 and R2 equal to p by 4. This was the first step in solving the problem. However, when we come to this, at the first step, if we wish to determine these unknown forces, we are not able to do that. Okay, because we have more unknowns compared to the number of equations of static equilibrium. So considering just the statics part, which you learned in your first year mechanics, this problem is unsolvable, which is why, or we cannot determine the solution of this problem, which is why it is referred to as statically indeterminate. We cannot determine it. Cannot determine means cannot determine using the methods of statics only. Does not mean that we cannot determine the solutions at all. Okay, and using deflections. Deflections means the information associated with the deformations, we can definitely find out the solution to this. Okay, so let's try to do that. So give me some idea. Okay, I don't know. Let's pretend that I don't know what to do. You tell me what I should do here. So you try to extend the ideas which you have learned in the statically determinate case to this thing. I'm telling you everything that is needed to solve this problem, you know. You just need to think a little bit differently. Just think for half a minute. Give me some ideas.
Sir,
Yes.
can we use like a superposition principle for this?
Superposition means what?
So like we will we can divide this problem into two separate problems. For the first one, we can remove the right hand side the wall, and for the second one we can remove the pin joint on the left and solve this separately, and then combine the pictures, and then finally input the boundary conditions that the y will be 0 for both the ends, moment will be 0 at the pin joint.
Yeah,
find
idea seems all right. Okay, idea seems all right, but the way that you suggested it, there is a little bit of an issue. You see, if I remove this wall, so this beam is pin supported at the left end, it will just fall down. No? If you want to consider this beam like this, okay, just this beam with this loading or whatever loading, okay, will it not fall down? Because this is an improperly or an incompletely constrained problem. Okay, just fall down. No? So using your ideas, you just try to modify what you're trying to say. Your idea is like the spirit of the idea is correct. You have to do something like that. Just think a little bit differently, or maybe anyone else, if you can extend the idea that was just presented, that we remove one of the sides and then maybe proceed. Suppose I just like take the other way around. Suppose I consider it like this. Then nothing is falling down. This is just a cantilever beam. Okay, this is just a cantilever beam. Okay, it is properly constrained and everything. It can stand on its own. The only difference from this is that the unknown reaction force which will be exerted by this pinned end on this beam, that has gone missing here. Okay, since that has gone missing, let us artificially put it like this. So we have some kind of a distributed loading, this triangular distributed loading present here that we have represented, and the influence of this reaction support that we just write in terms of this. So we call this RA. Now usually, like if this had to be a statically determinate problem, the value of this RA would be known to us beforehand. It would be given to us. But in this case, RA is not known to us. That is the only problem. Okay, if RA is known to us, then this is a straightforward problem. You just do this thing. Okay, take the moment, take any cut section, take the moment and just proceed. Usually you will get the answer. So what do you do to handle this unknown RA? So just try to think whenever you are faced like in this problem, in this kind of a situation, just try to proceed like you would usually proceed. Suppose you do take a cut section like this. Okay, suppose you do take a cut section like this, and then you isolate this out. Okay, so what is the actual difficulty? Like try to think about it in a pinpointed fashion. Where is the difficulty lying? You have a V, you have a M, all these things are same. Where exactly is your problem? Suppose I write the moment balance here. Okay, tell me what is the moment balance? So I have to represent this thing. Forget about this RA for the present. Okay, like just pretend that you somehow you know the RA. Then you tell me how you should go about solving this thing. Just tell me how do I find out how do I write the expression of the M? This is entirely X. Okay.
M minus RA into X.
M minus RA into X, then
minus
So plus L by 3 into
what L? How is L coming?
I mean x by 3. X by 3.
X by 3 into
W.
say what is the load over this? What is the entire
Sir,
load?
Wx by 2, sir.
W
X by 2.
Wx by 2. Yes. This entire distance is x. So if this had been a uniformly distributed load, this would have been a rectangle. The entire force due to that distributed load would have been W into x. But this is a uniform, and this is a triangular distributed load, so only half of that. So this is half of Wx. This is the entire force that is acting on this. This x by 3, remember what we did back when doing those problems in the shear force and bending moment. Okay, so for the benefit of the others, okay, who may be wondering what this x by 3 is, what we are doing is we are replacing this distributed load through this equivalent force, understanding that the location of this equivalent force will be this thing, where this is x by 3. Okay, this of course is 2x by 3. So this is x by 3. So we are taking the moment of this equivalent force about an axis which is passing through this right end of this cut section. So x by 3 into what is the magnitude of the force? It is half of Wx. So this thing should be equal to 0. So up to this point, we have proceeded exactly like in the statically determinate case. Only issue is that we don't know Ra. Okay, it is not known to us. Let it remain not known to us. Will not. I mean, so this M is equal to Rax minus Wx squared by 6. So the equation if we consider this version of the equation where we take the second order derivatives, this is going to be Ra into x minus Wx squared by 6. Fine. Now suppose we go one step ahead. Suppose we integrate this equation twice. Then what are we going to end up with? We are going to end up with an expression for this y. And this expression for the y, what are the unknown things that we are going to end up with here? In this expression, what are the
plus 2 arbitrary constant?
Yes, so we are going to end up with two unknown constants of integration and R. Very good. Okay, so you see how we have tried to boil down our problem to this statement that we have obtained the expression of this y, where unlike the statically determinate case where you just had two unknown constants of integration, we certainly have that here also, but in addition to that we also have the unknown Ra, and we can trace this unknown Ra to the fact that we are actually solving a statically indeterminate case. Question is finally, okay, so till now we have avoided dealing with the method which we should use to find this Ra. Now it is the moment of truth. How do we find out Ra? You tell me.
So just now we considered various boundary conditions.
Yes.
Here for the pin joint and for the clamped fixed end.
You tell me exactly what else should I use?
Sir, about the pin joint, we'll get a y equals to 0 and m is 0, considering at x equal to 0.
Okay, so at x equal to 0, y equal to 0 you are saying together with m equal to 0. But let us not forget that whether this is statically determinate or indeterminate, your beginning governing equation is this second order differential equation. Okay, so this equation is going to be helpful.
No, sir.
No, sir.
Yeah, this is not going to help us. Okay, it is true that m should be equal to 0 there. There is nothing wrong with that. But as far as our solution method is required. Okay, it is not going to help us. Okay, so we cannot use this thing. What else can I use? At x equal to L,
y equal to 0 and dy by dx is 0.
yes. So done. You see, in the expression of y, we have three unknowns. Okay, two unknown constants of integration and this unknown force Ra. And from the conditions, from the boundary conditions, we are actually ending up with two conditions. Three conditions. Okay, so we definitely have three conditions. So three unknowns, three conditions, you can find it out. Okay, now this problem has actually been solved in Beer and Johnson. Okay, as one of the example problems, which is why beyond this, I want to illustrate to you that this problem can also be solved in another way. Okay, so as you may have already guessed, I want to take up not this second order differential equation version of this problem, rather the fourth order equation. Okay, and this particular problem is especially suited to that to the use of that fourth order equation, because if I use the fourth order equation, the form for which is this. This is the general form of the fourth order equation. You see on the right hand side, I have the expression of the distributed loading. And the way that this problem has been given, the loading is actually a distributed loading. So it is as if like begging us to use this equation. The reason that I want to highlight to you is not just to give you an alternative method, but to also illustrate to you that some of the things which you had to worry about while solving this problem through this second order differential equation method, you probably won't have to think while doing this, while proceeding by this method. Let us see.
So I think you should be minus w by 3.
Which one?
Same last equation. ei d4 by upon dx to the power 4 is equal to minus w by 3.
It would be minus wx by L.
Oh, okay. So I wrote this the general version. Okay, the general. So this is general.
Okay.
Okay, so please note. Okay, I should have been more careful in writing this. So at this end, this is W naught, and the general expression for this Wx here is W naught x by L. Okay, this W naught has the unit of Newton per meter. Okay, so if you substitute x equal to L here, you obtain this W naught, which is the value at this x equal to L. And if you put x equal to 0 here, you get this W equal to 0, which is the thing here. Okay, so for our problem, we are going to end up with minus W naught x by L. This is what I'm going to solve. So I integrated once. You guys probably can do it faster than me on a piece of paper. Okay, my handwriting is not very fast on this writing app. So please do it on your own and verify that what I'm doing here is actually correct. So step by step, I'm integrating. Sorry. So everyone please check, I mean take a moment to please check, okay, that this is correct. And if it is not, tell me where the mistake is. Everyone please check if this is correct and confirm to me.
Yes, sir, it's matching.
Correct, sir.
What is the mistake?
So we said it's matching
Acha,
with us.
yeah, I think this is correct. All right. So we have this thing. How many constants of integration we have ended up with? 4.
4.
C1, C2, C3 and C4. Very good. So we have to use 4 conditions. Okay, now please note that in the previous version of our solution, from the very outset, we had to deal with this unknown constant, with this unknown force Ra. Okay, every step that we were taking, we were a little bit nervous what we do with this Ra. But now you see nowhere in this picture this Ra has appeared. Now some of you may be worried that earlier what I had told you about this problem, where there was this influence of this P, and I went, and if I went about taking this thing, using the, so if I directly set this W equal to 0 and I did not take this influence of this P, then everything would be wrong. So I had to take it. We did not do that, but we had to take it using the Dirac delta. Now, it's not the situation same here. Okay, so it is as if I have very, very joyfully I have solved this equation, but nowhere I have taken the influence of this Ra. So am I missing out on the influence of Ra? This is my question.
Sir.
Why not?
So because it's been included in the other constants, maybe.
Which constants? I have not written any constants till now.
Sir, if Ra is unknown, then why should we include that?
If the Ra is unknown, then?
And like, then why should we include that? Like in the other case, P is known, so we cannot neglect that.
Yeah, that is my question. We should not neglect the Ra. Okay, because whether you are taking the second order differential equation version or the fourth order differential equation, the physical problem is the same. Okay, here also. So let me just finish. So here also, in this version also, you are solving this exact same problem. Okay, but there is a subtle difference in what we are doing here and what was the earlier problem. Okay, where you had to consider the Dirac delta. So someone was saying something, please go ahead.
Yeah, so like I was suggesting that like I think that the Ra was like absorbed into one of the 4 constants that we had in the final equation.
Yes, yes. Not directly absorbed, but you will see what is going to happen. So let us proceed, okay? Instead of talking theoretically or in an abstract fashion about these things, let us actually try to solve this thing and see what is happening and where this Ra has gone. Okay, so we want to solve this equation. Solve this equation means we want to find out the values of this C1, C2, C3 and C4. So we have to use 4 conditions. What are the 4 conditions we can use? Tell me by looking at this.
There are 2 conditions. At x is equals to 0, y will be equal to 0 and m will be equal to 0.
You tell me one by one. So at x equal to 0, y equal to 0. Very good. Because that is
M equals to 0.
Actually, let me just copy this thing. Okay, I'm just flipping between the 2 pages. Yeah, tell me now.
M is equals to 0 and also.
At x equal to 0. Yes, very good. And please note that unlike before, I am very much allowed to use this m equal to 0. Allowed means this m equal to 0 does give me some useful information, because the governing equation that I have started out with is a fourth order differential equation. And this m equal to 0, it gives me a boundary condition where the order is 2, which is definitely less than 4. So this actually gives me a useful thing.
Yeah.
What else?
So at x is equals to L, y is equals to 0.
There is absolutely no doubt about it that since the beam is fixed to the right end at x equal to L, the deflection, that is y, should be equal to 0. So very good. This
And at x is equals to L, dy by dx is equals to 0.
very good. So this is a fixed end or a clamped end. And if we look at the boundary conditions which we had tabulated earlier, for the clamped end or the fixed end, we have these two conditions, y equal to 0 and dy dx equal to 0. That is all that we have written down here. Okay, at x equal to L, y equal to 0 and x equal to L, dy dx equal to 0. So we have these four conditions. Using these four conditions, we can find out C1, C2, C3 and C4. The moment we find this out, we can find out y. All nice and good. What happened to that RA?
So from bending moment equation in the previous case, we got moment in function of x, RA into x minus w x square by 6. We can compare that with the one of the equations in among the four equations which we got later.
The RA will be equal to C1, I guess.
Wait. Let me handle the suggestions one by one. So I think the first suggestion was that I considered something like this, right? This version, EI d square y dx square is this thing. And in the previous one, from the moment balance, I had obtained that RAX, this is equal to RAX minus WX square by 6. Of course, this is W naught, okay? All this is W naught. That is one of the suggestions. And the other suggestion was what? It is equal to C1. I don't know what you meant by that.
Sir, in the first equation, the dqy dx cube,
this one,
we can say that is equal to V, no?
Yes. So that this is the most direct way. Okay. So I think G. Saisaran, you mentioned this moment thing, right?
Yes, sir.
Yeah. So you give it a try. It should give you the answer, but the most direct, physically obvious thing would be to consider a cut section which is very, very close to this x equal to 0. So for all practical purposes, this is x equal to 0 plus that we are talking about. So what I'm suggesting is that for the purpose of determining RA, you take a cut section like this. So if you take the free body diagram of that cut section, the RA is going to be like this, and the V is going to be like this. And of course, you are going to have this M also. So if you take the force balance in the Y direction, it is going to be sigma Fy equal to 0, which will give us V is equal to RA. So RA is going to be equal to EI d cube Y dx cube in the limit x equal to 0. So please okay, so this is at x equal to 0. So if you set x equal to 0 here, this becomes 0 all you have is this C1. But please note that we have already determined the actual value of C1. So it will be something, okay? So I don't think I have that. So C1 will be something like W naught L by 10. Okay, so you will get the value of this RA as, I mean, in terms of the known things that are given to you as part of the question. So that's it. So earlier, someone had mentioned that the information regarding the RA is actually embedded within this C1, C2, C3, and C4. And as we have just seen, that is indeed correct. The RA is actually equal to that C1. Right. So you see, if we proceed by this fourth order equation, somehow I think, I mean, it may be my personal bias or something. I think this thing is slightly more natural and free flowing compared to the previous one. But it is a matter of personal taste. Okay. So do whichever way you feel more naturally inclined to. Okay, both of them are perfectly all right, perfectly equivalent also. So, but this is easier to code up symbolically. Okay, that much is true. All right. So we have, yes.
So other reactions at the fixed end can be obtained by our moment balance equation only now.
You can do that, or you can directly use these pieces of information also. For example, if you wish to find out the moment at x equal to L, all that you have to utilize is that you find this EI d square by dx square. This expression involving C1 and C2, both of which you know, and then you set x equal to L.
Okay, sir. Yes.
Yeah, but just be a little bit careful in the sense that when you write like this, okay, the sense of the moment that you obtain from this thing, because this is an internal moment, and the reaction thing will be opposite to that. Okay, so just be a little bit careful about the sense of the moment. Because see, here this V, it is actually pointing downward, and this RA is pointing upward. It did not matter here because we understand very clearly about the sense of these forces. The sense of the forces are always easier to understand and think about. But please be a little bit careful when you obtain the expression of the moment from these equations and then equate that to the external moment, external reaction moment that you will be obtaining here. Okay, so what I mean to say is that if you take a region very close to that x equal to L, you will be having something like this. So this is your M, and this will be the reaction moment. Okay. Okay, so just be a little bit careful what you are saying. Okay. So this is the general idea regarding statically indeterminate cases. Here, the way that the problem was set up, we had only one unknown or one extra unknown compared to the number of equations which was available to us, statically speaking, meaning that we had 4 total reaction unknowns, whereas we have 3 equations of static equilibrium. It can so happen that our statically indeterminate case is set up in such a fashion that the number of unknowns are more than that. For instance, this same problem could have been set up in a fashion that you have another maybe roller support in the middle. Okay, in which case you will have in total 5 unknown constants of integration, 5 unknowns, 5 reaction unknowns. Okay, but you have 3 equations. So in order to determine that, you will need extra conditions. Okay, so the problem of the category that I have just described that is referred to as a statically indeterminate problem of the first order or first degree, where you have 4 things compared to the 3. So the discrepancy is 1. For a problem like this, it is referred to as a statically indeterminate case of degree 2, because there are 5 unknowns, there are 3 equations, so the discrepancy is 2. But the ideas which you will have to use to solve this problem also, it is exactly like this. Okay. Now, within this scope of statically indeterminate problems, you can have some very sophisticated applications. A couple of them I have put in the tutorial sheet. We'll discuss that. But before we can go into those sort of things, I want to illustrate to you something going back to this to the statically determinate case only. Let me remove this thing. And I want to show that through an example. So this is one of the problems in the tutorial sheet, which I have not yet uploaded in the course website. I'll do that today. So you see, we have this kind of an arrangement. So the framework consists of 2 steel cantilevered beams, CD and BA. So this is one beam, CD. This is another beam, BA. And there is another beam, CB, which is just placed over these 2 beams. The CD beam and the BA beam, at the end of it, this BC or the CB beam is placed. All of them are made of steel, so they have a Young's modulus of 200 gigapascals. They also have, each of them has a moment of inertia about its neutral axis of this much value. We are supposed to determine the deflection at the center G of the beam CB. So this thing, this beam CB, at the center of it, we are supposed to find out the deflection. So just think about this problem for a minute and tell me, don't just think in terms of equations, just try to think about what is happening here, like physically what is happening here. Please note that both these beams, CD and the BA, they are like individually, they are cantilever beams. This, I don't know if it is visible through this shared screen, but there is this shaded portion here. Okay, that shaded portion represents that this CD and this BA are both cantilevered beams. So there is a wall present here to which this D end is fixed and this A end is fixed. So just think physically about the problem and tell me what kind of deflections are going on here.
So we can consider this case as sum of 2 cases, like the beam BC is deflected being supported by 2 ends, and we can also then add the deflection due to those cantilever beams.
Very good. Very good. That is the correct, thinking procedure. Okay, without even thinking about equations. So as a very, very important part of your training to be an engineer, this kind of a thinking is extremely important. Okay, you should get a physical feel of a particular situation just by looking at it. Always, it will not give you the correct understanding, but you should get some physical feel. So this is a relatively straightforward situation, meaning to say that you see there is this 75 kilonewton force being applied at the middle of this BC. Now, you can immediately understand that this 75 kilonewton force, because of the nice symmetry of the overall situation, it will be equally distributed at this end C and this end B. Okay, because this BC has to be in static equilibrium, and the only supports that this BC has is through its point of contact with this lower beam here and this lower beam here. So if you consider the free body diagram of this beam BC, is going to be like this. If you look at it from this end, this is BC. You have the 75 kilonewton force here. So you will have the reaction force here R1 and this R2, and R1 is going to be equal to R2 is equal to 37.5 kilonewton. Now, because you have this R1 and R2 equal to 37.5 kilonewton acting on this beam BC, individually, if you think about this CD and the BA, which are exactly identical to each other, and I can consider only one of them. So this is C, this is D, and please note that at the end D, you have the wall, which is represented by this shaded region here. So it's like this. The force acting at the end C is nothing but this force R1 itself. Similarly, if you consider the AB beam, it will be exactly like this, except that we'll have the force R2 here, but R1 is equal to R2. So it's like this, that this beam is going to bend down under the influence of this reaction under the influence of this R1 force, and when it bends down, because the beam BC is placed on it, that also moves down. Okay, so it's something like this, that it moves down like that, and please note that when I draw a diagram like this, this is extremely exaggerated. Okay, a steel beam would not deflect in such a huge fashion. It is only for the purpose of clarity of the diagram I'm drawing like this. There is only a very minute deflection here. Okay, so the beam which is placed just above it, that also moves down with it. And the way that I have drawn it, it may seem that this beam BC is going to fall off from this, but as I said, this is a highly exaggerated diagram. The slope here is not going to be so huge. Nothing is going to fall down. Okay, so even if you do not consider any deflection of this beam BC, because of the movement of the supports on which it is placed, because those supports are also in the form of beams, this entire BC beam that moves down. But over and above that, because of this kind of a situation, this beam itself, that is going to deflect like this. It is going to deflect like this. So there are two deflections which add up at the point G. First of all is the deflection due to the movement of this C and this point B downward. And over and above that, the deflection due to this 75 kilonewton force directly. So overall, we have to add them up. Okay, so this kind of an addition or superposition is literally referred to as the method of superposition. Okay, so it is referred to as the method of superposition. Now, what do we actually do in terms of like operations? Do we go about in this method of superposition? Do we actually go about solving each of the equations repeatedly? Like each time you face this problem, do you again start from the very beginning, solve this second order or the fourth order equation, do the entire thing? I mean, that would be a humongous task. Okay, so in real problems, okay, you will often see that these real problems, many of these common engineering situations are set up in such a fashion or designed in such a fashion that they can be considered to be literally the superposition of some of the very common simple situations which we have already encountered. What I mean to say by that is that you go back to the first example that we considered. This was a simple case of the cantilever beam, and I told you that please try to find out the deflection here. Okay, did you try to do this? Did you try to find out the deflection at the at this x equal to 0? If you have not done it, I mean, I told you the other day that after solving you will get like this. So this is one of the most important results in deflection of beams. Okay, so just like when you were first starting to learn calculus, you obtained the ddx of sin x and the ddx of cos x through formal methods, but after a week or so, you did it so many times that you could remember those results and you could utilize them as part of larger problems without going through the fundamental derivations each time. Similarly, for the case of ddx of x to the power n, without thinking now you can write those results down. Similarly, when you encounter these kinds of elementary situations, these are like fundamental elementary situations, you should be able to immediately recall in your mind that the deflection at this end where the tip loading is being applied is going to have a magnitude of PL cube by 3EI. The minus sign is only indicating that the deflection is taking place in the downward direction. So this is a very elementary result, and these kinds of results are often tabulated in your textbooks. Okay, so if you have been studying from Beer and Johnson, you can refer to one of the appendices which are near the end of the textbook. You will see a list of various deflections and slopes of the common beam situations with different boundary conditions. These kinds of things are actually available as engineers in an engineer's handbook, and they can refer to these things, where of course in that engineer's handbook much more data is present, much more number of cases are present, and the expectation is that you will refer to those fundamental solutions and consider the solutions to more involved problems by building up from those fundamental solutions. So for this problem, the CD deflection will be simply PL cube by 3EI. Okay, where this P will be this R1. Okay, so the deflection for the so let's say this, I'm writing this as delta C1 just to indicate that this is only one of the deflections. Okay, so this is going to be PL cube by 3EI. This is going to be equal to R1 into L. L is 4.8 meters. EI. E value is given to us, I value is given to us. So we know this. What about the other one? This G. What is this G? So this is this case. It is the simply supported case. So let's check if we have done this problem. Well, we have not directly done this problem. We have done a variation on that. Okay, so this P is present here with at a distance of L by 4, but this could easily have been at a distance of L by 2, perfectly symmetric situation. And in that case, the deflection is PL cube by 48 EI. I just remember it. Okay, I did not do it in my head. I just remember it. Okay, it is like that information you recall is just like mugging up. Okay, it is as good as mugging it up. Now, you don't always have to mug this up. What I have done is that, let me see if I have it. Just give me a second, okay? Sorry, not this one. Okay. So I hope all of you can see this page. This is the tutorial sheet number 8, which I have not yet uploaded.
Yes, sir, we can see it.
Yeah. So this table I have directly copy pasted from the book Mechanics of Materials by Hebeler. Okay. In fact, many of the problems I think you may have already realized by now that I have been putting many of the problems in the tutorial sheets from Hebeler's book, as well as from Beer and Johnson, but mostly from Hebeler's book. So I noticed that in the appendix of Hebeler, more number of cases compared to Beer and Johnson are present. So I have tabulated these things. And at least once in your life, you try to obtain these solutions. Okay. Try to, I mean, ideally you should be able to do all of these things, but do give it a try to some of them. Now, the case that we are concerned with for this particular problem we are doing is this case. Okay, where the applied force is absolutely at the middle, and for this the deflection is indeed PL cubed by 48 EI. Again, the minus sign is only because of the fact that the deflection is taking place in the downward direction. So in examinations, you are of course most welcome. In fact, I encourage you to keep on referring to these things, which is why now that you are not under any pressure of an examination, get yourself familiar with these fundamental solutions. Okay, so here you have many of the simply supported cases. In the next page, you have many of the cantilever cases. Okay, the most elementary which is this one, where you have this PL cubed by 3 EI. Yes.
Sir, actually, we have learned this simply supported case in the +1 chapter.
Which chapter?
So, like in +1, we had this present strain thing, like introductory course. Like in that, there was some formula like something like WL cubed by 4BD cubed by. I think it's the same formula.
In your class 11?
Yes, sir.
In which chapter?
Stress and strain, something like mechanics. Like I forgot the name, but it's related to stress and strain. Okay.
All right. Good. But I don't think they may have introduced the fourth order differential equation or the second order differential equation. They may have given that to some other.
They gave the formula only. That's all. For simply supported.
Okay. But for our purposes, like we'll have to build up the solutions using these various cases. Okay, so you see, this is one important case. This is another important case. Then if you have a distributed loading, you will have these various things. So you certainly do not have to mug up all of those things, but if you keep on using them for various problems, you will automatically start remembering them. Okay, so that's what I'm saying. So let me get back to this. So here for this, all that you have to do is this PL cube by 48 EI. And this thing is going to be equal to this 75 kilonewton. And L is again 4.8 meter. So the overall delta will be equal to delta G, this 1 plus delta C1. Okay, so you can find out this thing. That's it. Okay, so this is a very straightforward, simple situation, but you can have more involved situations and various other considerations also. So we'll continue discussing them in tomorrow's class. All right. Thank you very much. I'll try to upload the tutorial sheet today. All right, please go to your next class. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.